opposite direction because this is the direction of the current, so I just reverse the direction of the current. So the electrons are drifting with a velocity Vd. Now if they're drifting with a velocity Vd and I'm at rest, I can see the charges moving. But what if I, as an observer, am also moving with the mobile electrons, with the sea of electrons? I'm also moving, drifting as an observer just alongside, in tandem, in complete synchrony with the sea of electrons. So that I would say that the velocity of these electrons is really zero. So would I feel a magnetic field? But this looks really strange because a magnetic field produces a force, an electric field produces a force. So the force cannot change based upon an observer. If the observer is moving or is stationary, the physics cannot change. So how do we reconcile this concept of the relativity of velocity? This is a concept that I will delve in some more detail in a subsequent week. I would like to show you that magnetic fields are related to electric fields and they are combined through this general framework of special relativity. So magnetic fields are not something special. Magnetic fields can appear as electric fields. Electric fields can appear as magnetic fields. You can have a force that has an electric component and a magnetic component. When the observer is moving, all of the magnetic component disappears and all of the force appears due to electric contributions. So magnetism and electricity are welded together in a bond that is unbreakable, and that bond is called special relativity. In fact, you don't have to go to these exotic phenomena to understand special relativity. Magnetism is relativity, and it's something that is seen right in front of our eyes. Whenever you stick a refrigerator magnet on top of a refrigerator, it's relativity at work. So this is something that you should really aspire for. This is really something, sometimes it feels it's eerie, it's strange, it's queer, that whenever you look at a magnet, you have transformers, you have electricity, it's relativity at work. Alright, nevertheless, now we would like to make this formalism a bit more quantitative. And what we would like to do is that if I have a charge, a positive charge, say Q, and it's a point charge that is moving with a velocity v, which is of course a vector, and I'm at some point P, at some distance from the velocity, I would like to find out the magnetic field here. Just as if I have a point charge plus Q, which is at rest, at some point R, I can find out the electric field here. The electric field here is going to point in this direction, and it's given by Coulomb's law. The electric field is simply 1 over 4 pi epsilon naught Q over R squared, where R is this distance, in the direction of the unit vector pointing from the position of the charge to the point of observation. So this is the unit vector R. So this is Coulomb's law, correct? This is what we've learned about electric fields, E fields. Can we come up with a similar observation for the magnetic field? Remember, this is an empirical law. It's an observation which has now rose to the status of a Maxwell's equation, which is Gauss's law. The inverse square dependence makes the Gauss's law work. We've seen that. So this is now elevated to the status of a Maxwell's equation. This is the Maxwell's equation, the Gauss's law in disguise. Now, could we come up with a similar relationship to find out the magnetic field at this point P due to this moving charge? Yes, two scientists have actually done this task for us in the 19th century, and they were Biot and Savart. So this empirical observation, generally called the Biot-Savart law, is stated as follows. If I have this moving charge, I would like to find out P, the magnetic field at P. The distance between the charge and P is R. The unit vector pointing from the charge to the point P is R. once again. The magnetic field B due to this moving charge is given by mu naught over 4 pi. This 4 pi is for dimensional consistency and it makes mu naught take up a nice value in the SI. So I'm writing all the formulae in SI, in standard units. Mu naught over 4 pi, now this is a vector, I have to have a vector on the right hand side. So what I do, I take the charge Q, it's a scalar, the vector V, I take the dot product with the unit vector R, so its magnitude is just 1, and I divide by R squared. So this is the Biot-Savart law. Cross product, vector product. Alright, so it's a vector product, it's a vector. Let's look at the direction of the magnetic field in this particular configuration. First of all, we observe that the magnetic field has an inverse square dependence upon R. For this particular point charge that is moving, it has an inverse square dependence upon the distance from the line in which this charge is moving. Now V cross R, this is just a unit vector. How do I find out directions of vector products? I take my right hand, my palm or my hand is in the direction of the velocity, which is forward, R is downwards, so I rotate my fingers in the direction of R, the magnetic field points in the direction of the thumb. So in this particular case, the magnetic field is pointing into the plane of the blackboard, and anything that goes into the plane of the blackboard, I would denote this by a cross. So this V is into the plane of the blackboard. If I had a scenario in which I would have the same charge Q moving with the velocity V and my point of observation was above the point charge here. In this case, R is pointing in this direction. So V cross R, the thumb points out of the plane of the blackboard. So at this particular point, a magnetic field is pointing out of the plane of the blackboard. It's coming out. And this is exactly what we observed here. Previously, I drew the direction of the conventional current as this direction. So charges, positive charges are moving in this direction. Right? I just made two diagrams, so don't be confused. Positive charges are moving in this direction. Right? QV cross R would give me a magnetic field that points out here and a magnetic field that points inside here. Alright. So I have a charge that is moving with a velocity. I can find out the magnetic field due to that moving charge. But generally, we don't have solitary charges that are moving inside vacuum. That only happens in the case of an electron tube, such as a cathode ray oscilloscope, and I'll show you a demonstration for that as well. We generally have current carrying conductors. Now suppose a conventional current I flows inside this current carrying conductor and it's a steady current. So everything is in dynamic equilibrium. All the charges have been set up, the electric field is uniform, and it creates a steady current through this conductor. I would like to find out the magnetic field at point P. Now what I would like to do, I have moving charges inside this current carrying conductor. I would like to take a small section of this current carrying conductor. I call the length of this section dl. Alright? So this is a small section of the current carrying conductor. It's a small volume. Now if there are n charge carriers inside this small volume and each one of them is moving with a drift velocity, that's what the sea of electrons really is. Just due to this section of moving charge, just this section, there will be some field here. That since I have broken up this conductor into small segments, I would not call this field B, Rather, I would call it dB. dV. And it's a vector, of course. And it's given by mu naught over 4 pi, alright, QV. Now, there are not one charges, but a large number of charges. How many charges are there? Let's say we have capital N charges inside the small section that are contributing to conduction. So we have N charges. So the total charge inside this volume is NQ rather than Q. And the drift velocity is V. Crossed with R, which is just this unit vector, divided by R squared. And R squared is just this distance. This is R. So this is the infinitesimal magnetic field taking into consideration only a small section of the current carrying conductor. Now we also know that the total number of charges N would be given by small n, which is the number of charges per unit volume into the volume of this section. Suppose the cross-sectional area of this wire at this location is A, capital A. So this is going to be NADL. This means that dV equals mu naught over 4 pi N Q A V dL crossed with R squared. But what is NQAV? It's just the current. The current density J times A. Mu naught over 4 pi J, which is a vector, A dL cross with R for R squared. Correct? Now, it's conventional that J into A is a current, and we would like to do a barter trade here. I would like to put this vector sign on top of L here. So I would replace this JA with I, which is the current. This JA is simply the current, but I have to respect the vectorial nature of this quantity. So, but I is not a vector, so it's a scalar. So I will just shift this vectorial nature onto dl. So I have IDL. And now dl is a vector that points in the direction in which the current is flowing. Right? This is just a mathematical convenience. Nothing special about it. I've just shifted, I've put the onus of being a vector from the current density onto the length. I put in the directionality of current flow into this vector L. So this vector is now pointing in the direction which the current is flowing. So I have IDL crossed with R over R squared. This is also the Biot-Savart law. So this formulation, this prescription is really the same as this prescription, and both of these qualify as the Biot-Savart law. Now let's look at a practical example. Long, straight conductor, current carrying conductor. Now suppose I have a current carrying conductor that is vertically placed, right? And it's really long, and it's thin, and it's straight, and it's really long. But I cannot draw anything that's infinitely long, so I just truncate here because of my finitude. I just truncate here, and a current is flowing through this conductor. And suppose the direction of the conventional current is I here. And I would like to find out the magnetic field at point P. which is at some distance. Let's call this distance y0 from the current carrying conductor. And I choose my coordinate axis such that this is x, this is my y axis, and this is my z axis. And I would like to find out the magnetic field at point P. Alright? First of all, I would like to see what's the direction of the magnetic field. Now I break this current carrying conductor into small sections. For example, I consider a section here. Remember, this wire is electrically neutral. If you ignore the surface charges, a complete circuit will be totally neutral. So this wire is really electrically neutral. Even though charges are flowing, charges are also entering this wire from a battery. So this wire is electrically neutral. Now charges are flowing, and we consider a small section. The distance of this section, let's call this point the origin. Let's call this distance z. So this distance is really z squared plus y0 squared 1/2. And the length of this section, let's call it dz. So what's the direction of the magnetic field? IDL. So once again I can use this prescription. DL is now pointing, DL is my DZ, is pointing upwards. So DZ is pointing upward. My unit vector R is pointing like this. So IDL crossed with R, the magnetic field points into the plane of the blackboard at this point P. So the magnetic field is inwards. Take any section on this wire. Each section will produce a magnetic field that's inwards. If I take a section here, for example, IDL is still upward, R is still pointing in that direction, magnetic field is still pointing into the plane of the blackboard. So due to all of these sections, if I consider them individually, each one of them is contributing a magnetic field that's pointing into the plane of the blackboard. Even though the magnitudes could be different, but all of these infinitesimal fields are pointing into the plane of the blackboard. So let's find out the magnetic field in this small section. It's just going to be dB is just going to be mu naught over 4 pi I, dl is dz. This is a unit vector, so its magnitude is 1. I need to find out the angle between dl and r. Suppose this angle is theta. So what I have here, I have r that is pointing like this, and I have dz that is pointing like this. So the situation that I've created for myself is the following. This is my dz. This is my r. This angle is theta. So what's the angle between dz and r? It's 90 plus theta. This angle is 90 minus theta. This angle is 90. So this angle is 90. This is so this is 90 minus theta. This is 180 minus 90 minus theta, which is 90 plus theta. So this entire angle is 90 plus theta. So the angle between dz and r is 90 plus theta, and you really have to be careful about this. How do you find the angle between vectors? You join the vectors at their tails. You join the vectors at the tails and find out the relative angle. So here the relative angle between dz and r is 90 plus theta. So I have I dz sine of this angle. So the sine of this angle is cosine theta. So I dz cosine theta divided by the distance squared. Now the distance is z squared plus y naught squared under root. So this becomes z squared plus y naught squared. So this is the magnetic field due to just this section. Alright. Now if I would like to find out the magnetic field due to the entire length of the wire, I would break up this wire into smaller sections. And for each section, which parameter is actually changing? It's z. or theta. Z and theta are related. So the parameter, the running variable is either z or theta. I can put everything in terms of theta, for example. So by looking at this triangle, I notice that z equals y naught tan theta. So if I were to make the substitution that z equals y naught tan theta, which also means that dz equals y naught secant squared theta d theta, I can put all the z's, replace them with their theta counterparts, and the small field due to this one section that I will obtain will be given by mu naught over 4 pi I cosine theta. dz is replaced by this y naught secant square theta d theta. Here I would get z squared 1 plus y naught squared y naught squared 1 plus tan square theta, which is secant square theta, right? This secant square theta goes away, this y naught goes away, and I'm left with mu naught I cosine theta d theta 4 pi y naught squared. This is my dB. Y naught, sorry. Extremely nice result. First of all, you observe that the magnetic field falls off inversely as y naught. You go further away, the magnetic field drops, and it drops linearly. But this is just the magnetic field due to a small section. If this wire were of infinite length, I would have to integrate the contribution from each one of these small sections. The total field, magnetic field, will simply be given by the integral of dV. And I can perform this integration easily as scalars because all of these contributions are fields pointing into the plane of the blackboard. Remember, whenever I do integration, I have to respect the vectorial nature of the fields. Here, things are to my facilitation because all the fields are pointing in the same direction. So I can simply add them up. So this total magnetic field would be mu naught I over 4 pi, y naught is a constant, the integral of cosine theta d theta. Now if my wire were of infinite length, what are the limits for theta? Minus pi by 2 to plus pi by 2. Because if this were to go down and down and down, this angle would approach minus 90 degrees. If this angle would go up, 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 it would approach plus 90 degrees. So these are the appropriate limits. So I get a sine theta here, sine of 90 minus sine of minus 90 gives me a 2. So this becomes mu naught I over 2 pi y naught. This is the magnetic field. And if I would like to put vector signs with it, this is pointing into the plane of the blackboard. In my convention here, it's pointing into the plane of the blackboard. So it's pointing in the minus I direction, minus hat I, right? This is my magnetic field. And don't confuse this unit vector with the current I. Half a minute of silence and deep breath. And now what's going to come in front of you is something extraordinary. Alright, so let's see what's going on here. my magnetic field B due to a current carrying conductor is given by mu naught I times 2 pi y naught. Now y naught is the distance from a wire, and this field would be the same here. It would be the same at any point that is equidistant from the wire. It could be here, it could be here, it could be anywhere, because it's a long infinite wire, just like a sheet of charge. If you are at a distance from a sheet of charge, which is r, then your field is going to be lambda over 2 pi epsilon naught r. It's going to vary inversely as r. Here the magnetic field is varying inversely as the distance. Now what I would like to do, I would like to take this 2 pi y naught to the other side of the equation, and I would obtain B times 2 pi y naught equals mu naught I. Now let's, ये थोड़ा सा अभी बंद कर सकते हैं ताकि distraction ना हो. Now let's look at this formulation, this prescription, and I would like to look at this straight current carrying conductor from the top. So I draw a plane. I have a thin wire that is bringing current out of the plane, right? So current is coming out. So this is the direction of my I. Now I would draw a circle around this current carrying loop inside this plane. The circle is of course a closed path. It's a closed loop. The radius of this circle is r. Now at each of these points B is going to be constant, and the direction of this B is going to be tangential. I can use the right hand rule. Current coming out, the magnetic field here is pointing in this direction, here it's pointing in this direction, here it's pointing like this, just like a flywheel. So the magnetic field at each point is tangential. So I have a tangential magnetic field. Can I have a tangential electric field? No. If I do not have changing magnetic fields, the partial form of Faraday's law states that I cannot have an electric field that is tangential, but I can have a magnetic field that is tangential, and that is indeed what I have here. Okay? Now this is a tangential field, and the length of these vectors is the same, because the magnetic field only depends upon the distance. Each one of these points is at the same distance. Now if I were to look at this formula, I would have B. Let's call this field B1. The magnitude of this field B1. B1 into 2 pi R1. Let's call this R1 equals mu naught I. Alright? Now suppose I draw another circle around this current carrying wire, which is at a radius R2. The magnetic field will of course be different because it falls off inversely at the distance from the current carrying conductor. But now if this magnetic field is B2, which is again tangential, 2 pi R2, if I perform the same calculation, I would get B2 into 2 pi R2 is mu naught I. Both of the right hand sides are equal. This means that these left hand sides must also be equal. So what this tells us is that if I take B, the magnetic field, and I multiply it with the circumference of a closed loop, I'm going to get mu naught times the current that is inside the loop. B times the circumference equals mu naught times the current that pierces the area whose boundary is the circumference. Remember Gauss's law? Gauss's law states that I have a closed volume, a closed surface, sorry. I have a closed surface. The total flux that comes out of this surface, of this closed surface, is E dotted with small areas, d is integrated over the closed surface area. This is 1 over epsilon naught, the charge enclosed. Where is that charge? That charge is inside the volume which is bound by the Gaussian surface. So this volume has an outer surface and you find the flux through that surface. Like this room, this is a volume. We are all inside the volume. But the outer surface of this volume are just the peripheral walls. Alright? So this is Gauss's law. This law states that if I take the magnetic field B and find its dot product with a small section of length dl and integrate this over a closed path, this equals mu naught times the current enclosed by the path. This is called the Ampere's law. Now a few motivational examples around this. Let's look at the left hand side of the Ampere's law. B dotted with dl integrated over a closed path. So what does this really mean? This means that suppose I have a current carrying conductor that is bringing current out of the plane of the blackboard, and I have a circle around this of radius r. Now I've already found out the direction of the magnetic field. It's tangential to the points on the circle. And the magnetic field all around is constant. So what I would like to do, I would like to take the magnetic field at each one of these points and I would like to break up this loop in small segments. Each segment has a length dl. So I move around this loop in a counterclockwise fashion. So if the current is coming out of this plane and I move around this, I circumambulate this in a counterclockwise fashion like this. I go around it. Okay? Suppose my trajectory is circular as I have drawn here. So this circular trajectory can be broken down into small dls. Now B dotted with dl is a local dot product. It's a dot product here, there's a dot product everywhere. So it's a local dot product. Now B is tangential, dl is also tangential. Because the small sections in the circle, they are also tangential. So they are parallel to one another. Alright? So if I take the integral of this around the closed path, remember it has to be a closed path. It's a loop. In Gauss's law, it has to be a closed surface. This is a closed loop, a closed circuit. Alright? So this equals B times 2 pi r. Because both B and dl are locally parallel to one another. And then if I integrate, I get B times 2 pi r. Now this must equal, by virtue of Ampere's law, to mu naught times the current enclosed. Now what do we mean by the current enclosed? This path is on a surface and there is some area enclosed by the path, which means this path is on the outer periphery, it's on the perimeter of an area. I would like to look at the current that pierces this area, that comes out of this area. This is called the current enclosed. in the Gauss's law, I have the charge that resides inside a volume, that is bound by a surface. Here I have a path and I find out the area that is inside the path, and I look at the current that pierces this area. Alright? Now this is a nice circular path. What if my path is not circular? Rather, I break this path, make this path slightly tortuous, slightly wavy, like this. Now what's going to happen is, still this formulation will hold. It's going to hold true. Because if I take these small dls, I do not want to go over this again. If I take a small dl here, right, it's of course not tangential because the path is not tangential. The dl is pointing in this direction, but the magnetic field is pointing in this direction, and there is a certain angle. So if I take this B dot dl, the dot product, it's simply going to be B into dl cosine of the angle. And this is simply the projection of dl along the tangential direction. And that is simply equal to the arc length. It's simply equal to dr, the arc length. So if you integrate over the entire circle, you will still get B, you will still get something that is equal, whose integral is equal to mu naught I. So this path need not be circular. It could be any path. Suppose I have a situation like this, in which I have a current carrying conductor and I take a path like this. So I draw two arcs at different radiuses and my path goes like this. Now this is point 1, point 2, point 3, point 4. If I look at the left hand side of the Gauss's law, I have B dotted with dl from point 1 to 2 plus B dotted with dl from point 2 to 3. So I've broken up this my path into small 4 piecewise constant parts from 3 to 4, B dotted with dl plus 4 to 1, B dotted with dl. So this is the left hand side of Ampere's law. Now the magnetic field is always going to be tangential, right? So if this is my current carrying conductor, here the magnetic field on this path is going to be like this, along the tangent, along the tangent, along the tangent. Here it's going to be along the tangent, even though it's going to be smaller here because it's further away. Here it's also going to be like this. And here it's going to be like this. Now if you traverse this path, and if you go from 1 to 2, you get a negative contribution. Alright? This gives you a 0 contribution. From 2 to 3 it gives you a 0 contribution because your dLs are locally normal to the magnetic field. So this gives you 0. This gives you 3 to 4 gives you a positive contribution, whatever that is. And 4 to 1 gives you a negative contribution. Now let's see what happens to these contributions. Right? Now if this path is at a distance r1 and this arc, suppose it has a distance r2, and both of these are circular arcs. So I know that the magnetic field here is going to be different from the magnetic field here. So if I look at this integral from 1 to 2, my integral B dotted with dl equals, now from 1 to 2 the magnetic field is some B1, right? Let's call this magnetic field B1. This dl is simply R1, suppose this angle is, I call this angle here theta. Now this angle is the same for this arc as it is for this arc. Okay? So this B1 dotted with dl is the magnetic field here, which is B1 times this arc length. What's this arc length? R1 theta. So I have B1 R1 theta. Now from 3 to 4, the magnetic field and the direction in which I am traversing the path are the same. From 3 to 4, so there is a minus sign here. From 3 to 4, B dotted with dl is some magnetic field, which is B2, right? It's not going to be the same as B1 because the field here is going to fall off as compared to the field here. So it's B2 times R2 theta. Now if I look at the left hand side of Ampere's law, it's B1 R1 minus B2 R2 theta. Now we already know that B1 over B2, the magnetic field falls off like this. You are further away from the current carrying conductor, the field is smaller, and there's an inverse relationship. So B1 over B2 is R2 over R1. So I just put this in here. B1 over B1 into R1 equals B2 into R2. So I just insert this in here, I get 0. And indeed this should be the case, because if I look at this path, even though there is nearby current, but inside the area on whose perimeter lies this path, there is no current that's piercing this path. So around this path, the dot product of B dotted with dl when integrated around the closed path is 0 because it does not enclose any current. Quite nice. Likewise, if I have situations like this, I have a wire that is carrying current like this, I, and I take a surface, and on that surface I draw a closed path like this, and I go around this path in this fashion. Now this current is actually piercing the surface. Let me draw this in a more dramatic fashion. So this current coming in and it crosses the surface. There's a sheet of paper, and on that paper I've drawn a path, and this current carrying conductor just makes a puncture through that sheet and it comes out. So the field around this path, B dotted with dl, around this path will be mu naught times I. Now suppose I take the same path, I go around this path, and my conductor is not behaving properly, which means the conductor is coming out, then going back in, making a twist, coming back in, going out like this. Now I have a path and I have a surface that forms the inner region of this path, and I have a current that's coming out and a current that's going in. The total current that pierces this path is 0. So around this path For this particular configuration, B dotted with DL is going to be around this closed path is going to be 0. Now if I take the same current carrying loop, it's just the same current carrying loop, but I choose a different path. For example, the path that I choose is now like this. It's a different path. So it just falls short of the other arm of the conductor. Now around this closed path, B dotted with DL is going to be equal to mu naught times I. The same current carrying configuration, but I've chosen a different path. So around this path, this would hold. Remember that for any single point, if I take a point here, P, and I take the same point here, P, the magnetic field at both of these points will be the same. It's going to be the same. The magnetic field here at point R is going to be the same as the magnetic field here in both of these configurations. What is different is the line integral. The integral of the magnetic field with the infinitesimal distances integrated over the closed path. That's going to be different. Even though the magnetic fields at these points R will still be the same. So the Ampere's law's left hand side gives you a global picture. Just like E dot dA integral gives you a global view of the flux through a big surface. This gives you the line integral of the magnetic field through a complete closed path. Now, this actually is quite a wonderful picture here that we are slowly painting bits by bits. We are making a nest for our small sparrows to stay. It's तिनका करके छोटा छोटा एक आशियाना बना रहे हैं और देखिए हमारे पास कितनी ज्यादा चीजें आ गई हमारे पास गॉसेस लॉ आ गया E dotted with dA around a closed surface equals 1 over epsilon naught Q enclosed. E dotted with dl on a closed path gives me 0. This is a partial form of Faraday's law. We have A, B dotted with dl around the closed path gives me mu naught I. This is Ampere's law. Remember, we have 4 Maxwell's equations. The fourth equation that I can just state at this junction in time is that B dotted with dA about a closed surface, just analogous to this equation here, equals 0. The total magnetic flux through a closed surface is 0. And I'll explain what this means. This is Gauss's law for magnetism. This is partial form of Maxwell's law. This is, partial form of Faraday's law. Partial form, this is Ampere's law, which is a partial form of Maxwell's law. So all of these are 4 Maxwell's equations, even though partial forms of them, because we have to make certain corrections. We would like to see what happens when electric fields change in time, and what happens when magnetic fields or currents change in time. But I would like to close this discussion with another nice demonstration, and that will lead to a calculation that I'm going to perform in the next lecture. So what I have here is a current carrying loop, but it has a large number of wires on it, right? It's like a solenoid. It's not an infinitely long solenoid, it's just a solenoid. Alright, so what I'm going to do now, I'm going to disconnect this straight conductor. And I'm going to connect this to the solenoid. I'm going to connect the power supply or the current source to the solenoid. B dot mu naught I. And now what I have is, you can focus. This is my solenoid, and this is just a compass needle that can be brought towards the solenoid or it can be brought away. थोड़ा सा आगे आगे. Focus करो. आप focus करो. फोकस हो गया. हाँ ठीक, चलो और नहीं होता, जूम नहीं होता, और थोड़ा सा हो रहा है. All right, so now let's look at this configuration. I do not have a straight conductor here, rather I have a solenoid or a conductor that is looped around many times, so I have many large turns of this coil. Now the expectation is that this will also produce a magnetic field. So now if you observe here, this is the axis of the solenoid. I have this rail. If you observe here, this is the rail, and on top of this rail I have a compass needle. And the compass needle is perpendicular to the rail. The rail is in this direction, and the compass needle is, of course, in the north-south direction, whereas the rail is in the east-west direction. So this is the axis of the solenoid, and the rail is parallel to the axis of the solenoid, and the compass needle is pointing towards north. We have north over there, Qibla is over there, west is here. So now I would like to pass a current through this solenoid and see the direction in which this coil, this compass needle, is going to deflect. So I turn on my power supply and whether it's going to deflect at all. I turn off the current. Now it's off. It's in its equilibrium position. I turn on the current. It's going to oscillate. It's going to change its direction. The current is large. It's going to settle down in a new position, in the east-west direction. Previously it was in the north-south direction. So it has gone, there's a torque that acts on this compass needle because there has to be a magnetic field produced by the solenoid, and we have to work out the directions of this magnetic field. So I turn on the current again, it's going to rotate by about 90 degrees. So there's a large force or a large torque that acts on this compass needle. There's a torque, there must be some forces that are acting on this compass needle. Where are those forces coming from? They're coming from some magnetic field. So magnetic fields can apply a force. But can the magnetic field also do work? We have to see that. So now what I would like to do in the last step, I would just like to change the orientation of the current, which means I would like to change the direction of the current. I can either change the winding, the clockwise winding becomes an anti-clockwise winding, or I can change the polarity of the power supply so that the current runs around in the opposite direction. Now I'm going to do that. Now the needle goes in the opposite direction. Right? It's gone towards the east, towards the other direction, towards the west direction. The compass is opposite, but it's gone in the opposite direction now. The current, I drop the current back, it comes back to its original position. If I move this compass needle further away from the solenoid. I moved it further away from the solenoid. So now it's along the axis, but it's further away from the center of the solenoid. Now let's see what the deflection is going to be. The deflection is going to be feebler. It's going to be smaller. I move it further away, the field is going to diminish. So what is the dependence of the magnetic field on the distance from the center of a solenoid along the axis? So not only do straight current carrying conductors produce magnetic fields, but these coils also produce magnetic fields. And that's where we will discuss the field due to a current carrying loop, or the field due to a solenoid, or the field due to a toroid, as they have these large toroids that are used for fusion reactions, like the tokamak. So what I've done today is I've given you practical demonstrations as well as an overview of Ampere's law that describes that currents, steady currents, can produce magnetic fields, they can produce forces, they can produce torques. So the next lecture we're going to look at more examples, an example of a solenoid, a toroid, and we would like to see how forces act on charges that are moving inside a magnetic field. Thank you very much and see you on Tuesday.